My name is Jacob Magnon, and today we will be going over lab number 4 in Physics 2211, which covers oscillating spring motion. Let's get straight into it. Looking at the purpose of this lab, we are trying to demonstrate how spring and gravitational forces interact with each other. We're also going to see how the energy principle works with forces of potential energy. Finally, we are going to create a program that predicts the motion of our spring based on only a few initial conditions and constants. Looking towards the end of the lab, we will see how the change in total energy is always zero, while comparing motion plots of our program to the actual experiment. As far as the formulas that we should know going into this, there are quite a few. The momentum principle, velocity update, and position update equations are all familiar, and the energy principle will also be important in this lab. It is especially useful if we include all of our forces to be inside the same system. When we do this, we can say that the change in energy of the system is zero because there is no work being done on the system. Some more formulas to know are the potential energies for spring and gravity, shown here. Also important is kinetic energy and spring force. It may seem like a lot, but once we get into the coding, it will be fairly straightforward. Moving on to the process of this lab, the first step was to track a mass connected to a spring frame by frame using Tracker Online. Once this was done, the X and Y position info was downloaded for use in the GlowScript code. Using our knowledge of energy and motion, we then create the necessary lines of code to predict the oscillating spring motion and use the file of data that we just downloaded for comparison. Once we can compare the position graphs of experimental versus predicted motion, we will do some analysis at the end. Video tracker here. On the left, I have a screenshot of the motion of the mass, and on the right, I have the X and Y position plots that will be saved to a file. I also have noted the initial conditions below that will be useful when creating our code. Our time intervals will be made using this value right here, and our code will run for 9.2 seconds total. I recorded the initial position to be this, and our mass starts at rest, so the initial velocity is 0, and our mass is also given to be this. For the GlowScript code, the initial conditions of mass, position, and velocity are shown at the top here. Underneath that are the relevant constants, and on the right we see how to derive the spring constant and the relaxed length of the spring. The spring constant was derived using a formula I did not mention before, the period of oscillation formula. This is shown here and can be written to solve for k. The period of oscillation can be determined by using our tracker data to find the time between waves of oscillation, and I found this to be about 1.5 seconds. Next, to find L0, I found a point in the video where the spring was almost perfectly vertical and set the spring force equal to gravitational force. I can do this because at this point, both forces act only in the y direction. Then I used the formula for spring force and the value we found for k to solve for L0. Finally, at the bottom of the code, you can see our values of energy, which are all found by plugging in the formulas shown earlier. This next part of the code, we will find the forces acting on our mass and use the energy principle to find total energy. Note that our system includes the Earth, spring, and the mass, while nothing acts in our surroundings. Net force is simply gravity plus spring force, and we can set the sum of the equations for kinetic energy, gravitational potential, and spring potential equal to 0. Finally, the second picture at the bottom shows the code that will create plots of recorded energy. After running the code, we get these three graphs. The first is our change in energy graph, which shows the constant value of total energy, while all of its components are oscillating between positive and negative values. On the right, the top picture shows the x position comparison between our model in blue and the experiment in red, and on the bottom we see the y position comparison. Looking at the results, we can first notice that the total energy is always constant. This is because no matter what, the sum of our energies at any point will work out to be 0, even when they oscillate. The x position plot stayed similar throughout, however some of the values differed more towards the end. The y position graph had both plots oscillate at the same rate, however the predicted model had a much greater magnitude. Some possible sources of error are some misplacements in tracking, we didn't take into account drag, and some small estimation errors. Lastly, one question you may have is, did the energy principle hold up here? In short, yes, because our total energy plot never strays from 0. As shown below, the combination of the sums of the energy values will be the same. Another question you may have is whether choosing our oscillation period based on the x-plot or y-plot is important. This is also yes, because as you can see here, the period of oscillation was not the same for both. This will have an impact on your calculations for spring constant and other forces. These differences may be caused by multiple factors like the camera angle or some tracking errors. Anyways, that's it. Thanks for watching.